here we will see expansion of symmetric kernel and some related properties. So, expansion of symmetric kernel. Now we've already seen some properties of the symmetric kernel and some results. Okay, now let's see how to expand the symmetric kernel. Suppose you have a symmetric kernel. So let a x comma t be a non-null, non-zero, non-null symmetric kernel non-null symmetric kernel that has finite or infinite number of eigenvalues. So we don't know whether it's finite or infinite. So let us take a non-null symmetric kernel which has finite or infinite. Okay, if it is finite, doesn't matter actually. You consider a case where you are taking infinite number of eigenvalues and then you truncate it. That can be done. So let the eigenvalues be the eigenvalues be let us denote those eigenvalues to be like this, and of course we will have some condition on this: lambda 1, lambda 2, lambda 3, and so on. Let us take this as equation number 1. Now we are writing this in this way, let's say, such that suppose any of the eigenvalues repeated 10 times, then we are writing this lambda 1, lambda 2 10 times, and in fact lambda 1 will be equals to lambda 2, that will be equals to up to lambda 10. Okay, such that each lambda I is repeated as many times as its multiplicity. And further, when you have these eigenvalues, you can always arrange them in the ascending order of their magnitude. Okay, so also denumerate these eigenvalues as this, as it may be 0 also. So 0 less than equals to mod of lambda 1 less than or equals to mod of lambda 2 less than equals to something like this. And let us denote this equation by equation number 2. If you want to change this, you can first take this lambda i's and then you can write beta i's. All those things you can perform. Okay, now we have eigenvalues, so let us take eigenfunction. So let phi 1, phi 2, phi k, phi n, like k less than, of course. Let us take equation number 3, 1, 2, 3. b corresponding eigenfunctions, b corresponding eigenfunctions such that they are not repeated and phi i's, if you take all this phi i's, then it is linearly independent. Okay, now if you take this to each value of lambda k, if you take that equation 1 where we have denoted all these lambda k's to each value of lambda k in equation 1 or 2, we have just denoted those equation lambda I is in equation 1 in the ascending order of their magnitude. So to each value of lambda k in this equation 1 there exists one and only one by k in equation this equation 3. And if you when we have these eigen functions, we can assume that further we can assume that phi k are orthonormal. What are orthonormals? How you make a eigenfunction orthonormal? Those things you can check. Further, we can assume that phi k are orthonormal. We have proved the results before this. Okay. Now let lambda 1, which we have already assumed, lambda 1 be eigenvalue such that the corresponding eigenfunction, the corresponding eigenfunction is phi 1. That's what we have already assumed. Phi 1, lambda 1, phi 1, lambda 2, phi 2, and so on. Now using this lambda 1 and phi 1, let us define the truncated kernel, by if you remember, we have denoted those iterated kernels by k suffix n. Okay. Now here we are defining our truncated kernel by over here. We are writing this 1, 2, 3 in a bracket on the top. So let us define this k1 of x comma t is equals to k of x comma t So we already know what is k, so we know what is k1. And using this k1, let us define k2. So k2 of x comma t is equals to this k1 of x comma t, and then already we have phi 1 and phi 2. So sorry, phi 1 and lambda 1. So using this phi 1 and phi lambda 1, we will write this as phi 1 x, then phi 1 star t divided by lambda 1. This is a complex conjugate. So k2, we will define this truncated kernel k2 by k1 minus phi 1 star of t upon lambda 1. With this definition of k2, we can easily check that k2 of x comma t is normal, because already we know that k is symmetric. Again, you can say that k is symmetric, so k1 is symmetric, and by using these two definitions of symmetric kernels over there, we can you can easily check that k2 is also symmetric. So normal, it is symmetric, and hence have at least one eigenvalue, say lambda 2, and let phi 2 be corresponding normalized eigenfunction. Now here we know we have this phi 1 phi 2. Here phi 1 of x will not be equals to phi 2 of x, even if lambda 1 is equals to lambda 2. This fact we can easily prove. Okay, let's do that. For we will show that phi 2 is phi 1 cannot be the eigen functions for this k2. So let this for integral a to b k2 x comma t phi 1 t dt, and will be equals to, let us write here, equals to, when you put the value of this definition of k2, it will be put the definition of k2 and then open the integral, I mean split the integral. So integral from a to b kx comma t phi 1 t dt minus phi 1 x, you can just verify this, upon lambda 1 integral from a to b phi 1 of t phi 1 star of t. You can easily verify this. And since this lambda 1 and phi 1 are the eigenvalues and eigenfunctions of the kernel k respectively, this will be phi 1 x upon lambda 1, because phi 1 of x is equals to lambda 1 into integral this. So you can take this lambda 1 outside. And this will be equals to minus, since this is no, orthogonal or normalized we are seeing, then this will be 1 and this will be phi 1 of x upon lambda 1, and this will be equal to 0. Okay? And if this is equal to 0, then write that also here. This implies phi 1 is not eigenfunction of k2 of x comma t, and it's not the eigenfunction, then phi 1 of x not be equals to phi 2 of x, even if lambda 1 is equals to lambda 2. That's done. So that is the fact what I have proved. Phi 1 of x is not equals to phi 2 of x, even if lambda 1 is not equals to lambda 2. Now using this phi 2, let us define next. Define k3, the truncated kernel k3 of x comma t. You can pause the video and you can guess what you will define, how you will define by using the way we have defined our k1, k2, right? So this will be k2 of x comma t minus phi 2 of x into phi 2 star of t divided by lambda 2. And when you convert this into your lambda 1, phi 1, phi 2 and k, you put the value, the definition of k2, it will be kxt minus phi 1 of x, phi 1 star of t divided by lambda 1, and then this minus phi 2 of x into phi 2 star of t divided by lambda 2. And for simplicity, let's write this in the summation notation. This is k x comma t minus the 2, so summation, let us take I from 1 to 2, pi I of x, pi I star of t divided by lambda 1, lambda 2, so lambda. So using the same argument what we have discussed for k2 with the same argument as for k2 as above, this will give us lambda 3 and phi 3. So again we will have lambda 4, phi 2, phi 4 and k4, and continuing in this manner we will have different cases, two cases. Continuing this way, we have two cases. Let us take case by case. Case 1. So the process will terminate. There are two cases. The process will terminate, or the process will it will go on continuing. Okay. So case 1, process continues indefinite. It will go on continuing indefinite, and if the process continues indefinite, then there are infinite number of eigenvalues and eigenfunctions. Now you think, what about the case 2? Case 2 will be the process terminates somewhere. And if the process terminates somewhere, then what will happen? What will be the situation? You pause the video and then see what will be the situation, and then you continue. Right? Case 2. The process ends. Process ends after n steps. Is the process stops at n step, means you will have the truncated kernel kn plus 1 of x comma t, that will be identical equal to 0. And if that is 0, then the way we have defined our truncated kernel, this will imply our k x comma t minus summation will be equals to 0. When you take the summation on the other side, it will be equals to summation say k, say let us take I from 1 to n by k of x. I have taken I, so phi I of x into phi I star of t divided by lambda. And what we have achieved here is, this implies kernel k x comma t is degenerate kernel, degenerate, or we can say separable. That means you can write the function of x and function of t a finite sum. Okay. Now what we have done here is this: we can go through the statements what we have written, expansion of symmetric kernel. And when we have symmetric kernel, these things what we have defined. We have defined the truncated kernel too.